Usually when we think about a machine, there's this comforting expectation of rigidity.
Right. Yeah, it's fixed.
Exactly. Think about a classic car engine. You look under the hood and you see the steel pistons, right? The iron block, the gears. It's solid. You can point at it and say, there it is. That's what it does, and that's the shape it takes.
Yeah, it's fixed in its form, which inherently makes it highly predictable. I mean, you apply force here, a lever moves there.
Yeah.
The physics are entirely macroscopic and, tangible.
But then you step into the world of cutting-edge biomimetic engineering and autonomous systems, and suddenly that classic engine block just melts away, literally. We're looking at a technological landscape today that is completely fluid. Welcome to Science Pills.
It's a very different world now.
It really is. This deep dive features a serious and I think wildly interesting conversation about the latest facts and discoveries in autonomous weapon systems and shape-shifting materials. We are going to dive deep into the science of gallium-based liquid metal robots that can actually melt through bars.
Which is just incredible to see in action.
Oh, it's mind-blowing. We'll also get into the development of robotic Iron Man suits and the deeply ethical implications of prototype warfare. Plus, we'll explore the intersection of biomimicry and advanced weaponry, everything from vomit guns to sentient unmanned vehicles.
Yeah, it's a massive shift in how we even define a weapon.
Right. So, if you are joining us today, you are about to get a highly concentrated dose of the future. We've gathered an incredible stack of materials for you to pull this off. We have everything from military engineering blueprints from how stuff works to cutting-edge materials, science research on elastomers from ASME and Science News.
And we're also looking at a really provocative, deeply critical university thesis that explores the dark sociology behind these machines.
Exactly. It's a profound collection of data. We are going to be connecting the raw molecular mechanics of these systems to the artificial intelligence that acts as their brain and ultimately to the real-world consequences of unleashing them.
Yeah, we're tracing the whole path, from the lab bench to the battlefield.
It's a wild journey. We are talking about robots acting like the T-1000 from Terminator 2 and the incredibly profound ethical questions that arise when human beings hand over the kill chain to an algorithm. So, okay, let's unpack this. Let's start by looking at how the very nature of human conflict is driving the creation of this bizarre hardware.
Because before we even touch the AI, we really have to look at how military engineers are pushing the absolute limits of traditional physics.
Right, because for a long time, the history of weaponry was basically just a history of trying to throw metal at someone faster and harder.
Yeah, that's essentially the defining characteristic of kinetic warfare. It's always been a pursuit of mechanical efficiency. If you trace the historical trajectory of firearms, you see this steady march of industrialization applied directly to lethality.
Right, like go back to 1835, Samuel Colt invents his revolver. The big innovation there wasn't even just the rotating cylinder, right?
No, it was the interchangeable parts.
Exactly. It industrialized the firearm, so you didn't need a bespoke gunsmith for every single weapon. And from there, the mechanics just accelerate.
Yeah, you move from the revolver to the Gatling gun in 1862. And that used a hand-cranked mechanism to rotate multiple barrels for rapid fire.
Hand-cranked, which sounds so archaic now.
It does. But then the massive paradigm shift occurs in 1884 with Hiram Maxim. He invents the recoil-operated machine gun. Instead of a human turning a crank, Maxim figured out how to harness the kinetic energy of the bullet firing.
Like physical pushback.
Right, the expanding gases and the backward physical recoil. He used that to automatically eject the spent casing, load the next round, and recock the weapon.
Wow.
It's a self-sustaining mechanical loop. And that single innovation leads straight to the assault rifles of the 20th century, like Mikhail Kalashnikov's AK-47. The goal was always uniform, just put more metal downrange, faster than the adversary.
But, looking at the modern arsenal being developed right now, it feels like that old philosophy has been completely abandoned. We aren't just throwing metal anymore. We are manipulating the environment itself.
We're manipulating human biology, really.
Yeah. Take the PHASR, for instance, the Personnel Halting and Stimulation Response Rifle.
Which is a fascinating departure from kinetic force.
It looks like a giant, bulky, sci-fi laser gun. And that's because it basically is. Developed by the Department of Defense, it's a non-lethal weapon designed to temporarily blind and disorient targets. But it doesn't just shine a bright light. It fires focused laser beams at alternating wavelengths.
Right.
So how does that actually stop a person in their tracks without physically hitting them with a projectile?
Well, it comes down to overwhelming the visual cortex. The human eye is, adapted to process specific frequencies of light at a manageable rate.
Sure.
The FEHASR emits a two-wavelength laser system. By rapidly alternating these wavelengths, it creates an intense strobing effect that the photoreceptors in the retina simply cannot process.
So it just glitches out your brain.
Essentially, yes. This sensory overload short-circuits the visual pathway to the brain. You are rendered completely disoriented, you're unable to stand balanced, let alone aim a weapon.
That is terrifying.
It is. The engineering challenge, of course, was calibrating the lasers to ensure this temporary blinding doesn't cross the threshold into permanently burning the retinal tissue.
Right, you're turning the target's own sensory organs into a vulnerability. But, not everything in the modern toolkit is non-lethal. Some of the kinetic weapons they tried to develop were just terrifyingly extreme in their own right. Have you seen the specs on the golf ball grenade?
Yeah, the V40 fragmentation grenade.
Yes. It was literally the size of a golf ball, 2.5 inches high, 1.5 inches in diameter. Soldiers in the 1960s and 70s called them mini frags.
Which sounds almost cute, but they absolutely were not.
Not at all. The idea was that you could carry a whole pocket full of these things. But despite being tiny, the explosive yield was lethal up to a radius of 5 meters, and fragments could be dangerous up to 300 meters away. But they had to discontinue them because the handling dangers just became too extreme.
Yeah, this is a perfect example of the limits of mechanical miniaturization. When you shrink a highly explosive kinetic weapon to the size of a golf ball, you also have to miniaturize all the mechanical safety mechanisms.
Right, the pins and springs.
Exactly. The safety pin becomes incredibly thin. The internal spring driving the striker becomes highly compressed in a tiny housing. And the chemical fuse time was incredibly short.
So it's just inherently unstable.
Highly unstable. Because the components were so small, they were prone to mechanical failure pins, bending or slipping, meaning the grenade could go off in a soldier's pouch with almost zero warning.
Oh, wow.
It's a prime example of where the pursuit of extreme mechanical convenience ends up creating an unacceptable, chaotic risk to the operator.
So to mitigate operator risk, you get inventions, like the corner shot. This addresses the age-old problem of urban warfare, right? Like, how do you shoot around a corner without poking your biological head out and getting shot yourself?
Yeah, and the engineering solution there is brilliantly simple but highly effective. The corner shot places a physical hinge in the center of the weapon chassis.
So the gun actually bends in half.
Exactly. The front half of the weapon, which holds a semi-automatic pistol or even a grenade launcher, pivots to the left or right. The back half, where the operator holds the grip and trigger, remains straight.
But how do they aim it if the barrel is pointed around the wall?
A high-resolution camera is affixed to the pivoting front section, and it feeds video back to a digital screen for the operator. You achieve line of sight and line of fire while your physical body remains protected behind concrete. It totally decouples the human eye from the barrel of the gun.
That makes total sense for urban combat. But let's go back to manipulating biology, because the weapons that truly mess with the human body are the extreme, non-lethal ones. We have to talk about the active denial system.
The heat ray.
The heat ray. Military officials apparently dubbed it the goodbye effect. This thing transmits an invisible beam from up to 500 yards away, and it instantly heats a person's skin to 130 degrees Fahrenheit.
Which is incredibly painful.
I can't even imagine. What is the physics behind making someone feel like they are on fire without actually burning them to a crisp?
It utilizes dielectric heating. The active denial system emits a high-frequency millimeter wave electromagnetic beam, specifically at 95 gigahertz.
Why that specific frequency?
That specific frequency is crucial. Unlike a microwave oven, which operates at a lower frequency and penetrates deep into organic tissue to cook it from the inside.
Yikes.
Yeah, we don't want that. But the 95 gigahertz wave only penetrates exactly 164th of an inch into human skin. That is just deep enough to reach the epidermis where the water molecules and pain receptors are located.
Oh, I see. So it's targeting the water in your skin.
Exactly. The electromagnetic wave causes the water molecules to vibrate rapidly, generating intense friction and heat.
Wow.
It triggers an immediate, overwhelming pain response. They compare it to the feeling of touching a hot light bulb that forces a physiological reflex to flee. It weaponizes the body's own nervous system against itself.
But it doesn't cause lasting damage.
It doesn't cause third-degree burns because the penetration is so shallow, but it achieves complete environmental dominance. You control the space because no one can stand to be in it.
And if you thought the heat ray was intense, the Navy contracted a company in 2007 to develop a vomit gun.
Yes, the biological hacking tools.
It sounds like the six sticks from the movie Minority Report. It uses radio frequencies to directly impact a person's equilibrium. And the Department of Homeland Security worked on an LED incapacitator that emits rapid pulses of different colored lights. So you look at a light or you get hit by an invisible radio wave and you just instantly throw up?
Right, because this targets the vestibular system in the inner ear, which controls our sense of balance.
How does light affect your ear, though?
Well, our brains maintain equilibrium by constantly synthesizing visual input from our eyes with the physical sensation of gravity and movement from the fluid in our inner ear.
Okay, that makes sense.
So if a weapon can emit a specific strobe of colored lights or a targeted radio frequency that disrupts the fluid dynamics in the ear, it creates a massive sensory mismatch. The eyes are telling the brain one thing, while the inner ear is screaming another.
And the brain just hits the panic button.
Precisely. The human body's evolutionary response to this profound neurological confusion is motion sickness and violent immediate emesis, vomiting.
It is literally physiological hacking. But,
Yeah.
Just when you think they've moved totally away from kinetic force, you see the bleeding edge of it making a massive comeback with the electromagnetic railgun.
Oh, the railgun is a completely different beast.
It entirely discards the concept of gunpowder. We are talking about using a massive electromagnetic field to accelerate a solid projectile to Mach 8. That is 8 times the speed of sound, or roughly 5,000 miles per hour.
Yeah, this relies on the Lorentz force. You have two parallel conductive rails. You introduce a massive electrical current that flows up one rail, across an armature connecting them, and down the other rail.
And that creates the magnetic field.
Exactly. It creates an immense magnetic field. The interaction between the electrical current and the magnetic field generates a propulsive force that pushes the armature and the projectile sitting in front of it forward at hypersonic speeds.
And the craziest part is that the kinetic energy generated at that speed is so devastating that the projectile doesn't even need an explosive warhead. The sheer force of the impact, a solid tungsten rod hitting a target at Mach 8, is enough to vaporize anti-aircraft missiles or enemy ships from miles offshore. Just pure, unadulterated physics.
It's kinetic energy at its absolute peak.
I actually loved a tiny detail about the power source for this railgun in the sources. It requires so much electricity, like enough to potentially launch a small payload into orbit, that the internal power device is officially called a flux capacitor, literally borrowing the name from Back to the Future.
It really highlights how the line between pop culture science fiction and actual defense engineering has essentially vanished.
Speaking of sci-fi, we have quantum stealth. The military is developing technology that bends light around an object, turning soldiers or vehicles completely invisible to the naked eye, like the cloaking device from Predator.
Yeah, this involves metamaterials or highly advanced lenticular lenses.
Lenticular lenses, like those ridged plastic cups from the 90s where the image changes when you tilt it.
Similar concept, but engineered at the nanoscale. Structure smaller than the wavelength of light itself. By doing that, you can dictate how light waves bend and refract. If you can channel the incoming visual spectrum around an object so that it continues on its original path on the other side, the object occupying the space in the middle simply ceases to visually exist.
That's incredible. It completely negates all traditional physical security and surveillance.
It does. It renders cameras and eyeballs completely useless.
And combining all of this, you have Talos, the Tactical Assault Light Operator suit, the Pentagon's literal Iron Man suit. It is a robotic exoskeleton that monitors vital signs, increases physical strength, and withstands bullets. But the real mind-bender is the report that future generations of this suit will use a liquid metal that can solidify into an impenetrable armor on command.
And, that transition from a rigid exoskeleton to liquid armor is the perfect pivot point for our entire discussion.
How so?
Because whether it is a railgun, a corner shot, or a traditional exoskeleton, they all suffer from the same fundamental flaw. They rely on rigid mechanics, hard metal, fixed gears, unyielding hinges, and rigid structures have severe limitations when they interact with a chaotic, unpredictable world.
Wait, let me float an analogy here. Let's look at the Armatics digital revolver before we totally abandon rigid weapons, because this pistol is fascinating.
Okay, let's hear it.
It has a digital safety mechanism. It only fires if the operator is wearing a specific smartwatch that sends an unlock signal via radio frequency, and the watch only activates if it reads the owner's fingerprint. So it's exactly like setting up two-factor authentication, but for lethal force.
There's an excellent way to frame it. Two-factor authentication for a firearm. It is an attempt to use digital logic to solve a physical security problem, preventing a stolen weapon from being used against the person who brought it to the fight.
But to your point, it still relies on a rigid mechanical form. A gun is a gun. A steel exoskeleton is still a stiff steel cage.
Exactly.
If you want to truly dominate complex, unpredictable environments, say, traversing through the jagged rubble of a collapsed building, or navigating a probe through the delicate pathways of the human circulatory system, machines must stop acting like metal boxes. They need to start acting like living organisms.
Precisely. Because a rigid industrial robot is incredibly efficient on an assembly line, but it is dangerous to humans. If a fast-moving, heavy steel robotic arm collides with a human worker, the human breaks.
Right. Flesh loses to steel.
Always. Furthermore, a rigid robot cannot compress its volume. It cannot squeeze under a closed door or contort itself through a narrow pipe. So to solve this, engineers turn to biology for the ultimate blueprint, birthing the field of soft robotics.
Because animals and plants don't have metal gears. They are squishy, compliant, and flexible. I was fascinated by the mechanics of how plants move in these sources. Plants don't have muscles or nervous systems. So how does a sunflower turn to track the sun? It relies on hydrostatic pressure, specifically something called osmotic potential.
What's fascinating here is how brilliant that biological mechanism actually is. A plant cell is essentially a rigid cell wall containing a flexible membrane filled with fluid.
Like a water balloon inside a cardboard box.
Exactly like that. The plant can actively adjust the concentration of ions like potassium inside specific cells. This changes the osmotic balance. Water rushes into the cell to balance the concentration, drastically increasing the internal fluid pressure, known as turgor pressure.
Oh, I see.
And this causes that specific side of the plant stem to elongate and bend.
So engineers are taking that exact concept and mimicking it synthetically. They are building robots out of soft resins and polymers, designing them with multiple internal fluid sacs separated by semi-permeable membranes. By actively pumping fluid or air into these specific chambers, they generate localized pressure.
Right.
This forces the soft elastomer to bend, twist, or wrap around an object, just like a vine wrapping around a trellis.
And they are also looking deep into marine biology. There is an ongoing project involving Cornell University and NASA to build soft robots inspired by lampreys and cuttlefish.
And the objective there is to design a machine capable of swimming through the subsurface oceans of Jupiter's moon, Europa. But why not just send a miniature submarine? We know how to build those.
Well, a traditional metal submarine is bulky, incredibly heavy, and requires massive amounts of electrical power for its rigid propellers and ballast tanks. Getting that mass all the way to Jupiter is economically and physically prohibitive.
That makes sense. The fuel cost alone would be astronomical.
Exactly. But a soft, undulating cuttlefish robot made of lightweight polymers can swim using a fraction of the energy by mimicking the efficient, wave-like propulsion of marine life.
They even built a self-powered soft robot inspired by a manta ray that actually survived a dive into the Mariana Trench, the deepest, most crushing part of the Earth's oceans.
Which is an incredible feat of engineering.
It is. Instead of trying to build a metal hull thick enough to withstand thousands of pounds of pressure per square inch, they just made the robot squishy. They distributed all the fragile microelectronics sparsely within a highly pliable silicone body.
Because the silicone is incompressible.
Right. It naturally equalizes with the surrounding water pressure, so the robot wasn't crushed. And there was Draybot, a dragonfly-shaped soft robot created at Duke University, designed to gracefully skim over water without disturbing the surface tension, monitoring for oil pollutants and acidity changes.
But imagining these creatures is one thing. Manufacturing them is entirely another. You cannot take a block of soft, wobbly silicone and put it in a traditional CNC milling machine or hit it with a drill press.
Right, it would just shred.
It'd be a mess. So the material scientists developed entirely new fabrication methods. One of them is shape deposition manufacturing, or SDM.
How does that work?
This is a cyclic additive and subtractive process. They deposit a layer of soft liquid polymer, let it cure, machine the edges, then embed a rigid component like a delicate computer chip or a sensor directly into the polymer.
Okay, so it's baked right in.
Yes. Then they pour a sacrificial support structure, machine it again, and pour more polymer. Once the support material is dissolved away, you end up with a single, seamless block of flexible rubber, where the electronics are perfectly entombed and protected inside.
Wow. Another breakthrough I saw was the Smart Composite Microstructure Process, SCM. This is vital for building tiny insect-scale robots. what they call mesoscale machines. At that tiny scale, traditional metal pin joints are too heavy and have too much friction, right?
Correct. So SCM combines microscopic rigid bodies made of carbon fiber reinforced polymer, linking them together with microscopic flexible polymer ligaments that act as the hinges.
And the entire sheet is laser machined and laminated together, allowing for incredibly complex, origami-like folding structures.
And of course, there is 3D printing, but not printing hard plastics. They use a technique called direct ink writing, or robo-casting.
Which is basically 3D printing with liquid rubber.
Essentially, yes.
Mm-hmm.
They literally 3D print intricate, fluidic elastomer actuators using custom-formulated silicone inks. You can print a soft robot with a complex maze-like network of internal air chambers.
So when you hook it up to an air compressor, those specific chambers inflate, causing the printed tentacle to curl and grab an object with an incredibly delicate touch.
And that brings us to how these soft robots actuate, how they physically move. The material science here is incredibly dense. One of the primary methods is dielectric elastomer actuators, or DEAs.
How does a DEA work? Because it sounds like you're just electrocuting rubber.
That is essentially what is happening, but highly controlled. Think of a DEA as a flexible capacitor. You have a very soft, highly stretchable polymer membrane sandwiched between two compliant conductive electrodes. When you apply a massive high-voltage electric field across those electrodes, positive and negative charges build up on either side of the polymer. These opposite charges interact each other with immense force, known as Maxwell's stress.
Oh, so the charges are pulling toward each other through the rubber.
Yes. This electrostatic attraction literally squishes the soft polymer membrane down. Since the polymer is incompressible in volume, as it gets thinner, it physically has to expand outward, stretching its surface area.
And they can stretch over 1,000% of their original size. You turn on the voltage, the rubber flattens and expands. You turn it off, and it snaps back. It is artificial muscle.
It is. But the glaring downside of DEAs is the power requirement. They need massively high voltages, thousands of volts, to generate that electrostatic squeeze.
Which sounds incredibly dangerous.
It can be. That can cause electrical breakdowns, sparks, and leakage currents. And practically, it is incredibly difficult to strap a massive high-voltage power supply onto a tiny, soft, cuttlefish robot. So they look to other methods, like shaped memory polymers.
Right. Shaped memory polymers, or SMPs, rely on thermodynamics rather than high voltage. These materials possess a specific glass transition temperature. I love the analogy for this. It's exactly like the classic toy shrinky dinks.
Precisely. At room temperature, the polymer chains are tangled and rigid. But if you heat the material above its glass transition temperature, those molecular chains gain enough thermal energy to slide past one another. The material becomes highly malleable.
So you can stretch it, twist it, and manipulate it into a completely new shape.
And if you hold it in that new shape while it cools back down, the chains lock into place. It remains rigid in that temporary form indefinitely.
But the magic trick is that the material's molecular structure remembers its original permanent shape.
Exactly.
The moment you expose it to heat again, hitting that transition temperature, the polymer chains violently untangle and the material physically snaps back to its original form. They use this for self-deploying structures in space or medical stents that you compress, insert into a vein, and then body heat causes them to expand and hold the vein open.
They also utilize pneumatic artificial muscles, which are essentially flexible tubes encased in a braided mesh. You pump them full of compressed air, and as the tube expands radially, the mesh forces it to contract longitudinally, perfectly simulating the contraction of a human bicep.
Those are controlled by highly complex algorithms, right?
Yes, PID controllers to manage the delicate airflow. But if we look at the absolute bleeding edge, researchers aren't just mimicking biology with silicone and air, they're actually incorporating living flesh. Biohybrid actuation.
This is where the line between machine and organism vanishes. They are literally building robots out of living tissue.
It sounds like science fiction, but it's happening.
There is a tiny jellyfish robot built by combining a soft silicone scaffold with dissociated rat tissue. They cultured rat muscle cells onto the flexible elastomer. When they applied a mild electric field to the water, the living rat muscle cells contracted simultaneously, and the robot physically swam and propelled itself forward.
And the researchers advanced this concept significantly with a phototactic stingray robot. They built the skeletal body out of a flexible gold structure and layered it with living cardiomyocytes heart muscle cells.
Just standard heart cells.
No, these have been genetically engineered to be optogenetic, meaning they respond to specific wavelengths of light.
Wait, hold on. You're talking about stringing together genetically modified rat heart cells and soft silicone and steering it with a flashlight.
That's the reality of the experiment, yes.
But how on earth does that survive an actual environment? If we are talking about deploying these in military applications or deep-sea exploration or sending a soft robot to Jupiter's freezing moon Europa, wouldn't a robot made of soft rubber and heart cells just shatter the second the temperature drops? Or tear apart after a few days of use?
You have identified the exact critical mechanical vulnerabilities that materials scientists are desperately fighting to solve. Soft robotics face massive inherent hurdles. The first is fatigue failure. Because these robots move by constantly bending, stretching, and squishing, the materials undergo intense cyclic loading.
Like taking a metal paperclip and bending it back and forth 50 times until it finally snaps from the stress.
Exactly. But on a macromolecular chemical level, the long molecular chains in the polymers physically wear out, detangle, and tear over millions of repetitions. The material simply degrades.
And what about the cold?
Second, and much more critical for an environment like the subsurface oceans of Europa or a high-altitude drone, is the issue of extreme cold causing brittle failure.
The ductile to brittle transition temperature.
Correct. At room temperature, elastomers are rubbery because there is enough ambient thermal energy for the polymer chains to remain flexible and slide past each other. But when the ambient temperature drops below a certain specific threshold, the material undergoes vitrification.
Vitrification.
Yeah, the thermal energy dissipates, the molecular chains lock rigidly into place, and the material instantly transforms from a stretchy rubber into a substance as brittle as glass. Any mechanical stress applied at that point will cause it to shatter catastrophically.
And there is a chilling real-world example of this exact physics failure: the Space Shuttle Challenger disaster.
A tragic, perfect example.
The O-rings that sealed the sections of the solid rocket boosters were made of a rubber elastomer. But on the morning of the launch, the ambient temperature was unusually freezing. The rubber dropped below its transition temperature. It became rigid and brittle, completely losing its elasticity.
Right, and when the immense pressure of the rocket ignition hit those O-rings, they couldn't flex to seal the gap.
The hot gases escaped, leading to the catastrophic explosion. So the stakes of material failure here are absolute life and death.
Which creates a massive structural dead end for engineering. Relying purely on soft polymers means your robot is too weak, vulnerable to tearing, and fundamentally compromised by cold temperatures. But relying on rigid metals means your robot is too stiff, too heavy, and lacks the adaptability to traverse complex environments.
And that answers the challenge. If soft polymers are too weak and rigid metals are too stiff, the holy grail of materials science is a material that can fluidly switch between both states at will. Which brings us to the liquid metal breakthrough. Here's where it gets really interesting. We are talking about the T-1000 from Terminator 2 becoming a documented reality.
And the foundation of this breakthrough is an element called gallium.
Gallium is mind-blowing. It is a post-transition metal, and crucially, it is non-toxic, unlike mercury.
Yes, very important distinction.
But its atomic structure gives it a melting point of just 29.8 degrees Celsius. That is 85.6 degrees Fahrenheit. If you take a solid, hard chunk of gallium and just hold it tightly in the palm of your warm hand, your sheer body heat will cause it to literally melt into a silver puddle of liquid metal.
However, gallium by itself is just a passive metallic puddle. You cannot issue a command to a puddle. To transform it into a smart, shape-shifting material, researchers at Carnegie Mellon and Sun Yat-sen University had to engineer an incredibly ingenious composite.
What did they do?
They took the liquid gallium and uniformly embedded it with highly magnetic microparticles made of a neodymium iron-boron alloy.
So now you have a liquid metal that responds to magnets. But how do you make it turn solid and then melt again on command without tossing the robot into an oven?
They utilize a physics principle called induction heating. By exposing this gallium composite to a rapidly alternating magnetic field, the embedded neodymium iron-boron microparticles begin to react.
Wow.
Yeah. The alternating field causes these magnetic particles to vibrate at a microscopic level and generates eddy currents within the metal. This rapidly generates internal heat through magnetic hysteresis and Joule heating.
So it's heating up from the inside out.
It is the exact same underlying physical principle as a modern induction cooktop, heating up a cast iron skillet.
Right. That makes sense. So they aren't blasting the metal with a blowtorch from the outside. They hit it with an alternating magnetic field. The tiny particles inside the gallium vibrate and heat up, and the metal literally melts from the inside out in a matter of seconds. And because those particles are magnetic, once the gallium is in a liquid state, the researchers can use permanent magnets to drag the fluid metal around, stretch it out, split it into multiple puddles, and merge it back together.
And the moment they turn off that alternating magnetic field, the internal induction heating instantly stops. The gallium rapidly dissipates its heat to the surrounding room temperature air, dropping below 29.8 degrees, and crystallizes back into a hard, rigid, load-bearing metal.
This led to the most visually stunning experiment I've ever seen, the jailbreak robot.
Ah, yes, a brilliant demonstration.
The researchers molded this gallium composite into a little solid Lego-like figurine and locked it inside a miniature jail cell made of plastic bars. Then they activate the alternating magnetic field. You watch the toy figure heat up and melt into a sludgy puddle of liquid metal. Then, using a permanent magnet placed outside the cell, they drag that liquid puddle smoothly through the narrow gaps between the jail bars. Once the puddle is completely outside the cell, it flows into a small plastic mold. The magnetic field is turned off, it cools down, and it reforms back into the solid Lego figure. It's completely wild. It is literally shape-shifting technology.
It is the ultimate manifestation of phase-shifting mechanics. And the practical applications go far beyond theatrical prison escapes. Think about the biomedical potential.
Like what?
The researchers simulated this by guiding a solid, pill-shaped gallium mass through a labyrinthine model of a human stomach to locate a swallowed foreign object, like a toxic button battery.
Oh, that's incredibly useful.
Once the gallium pill reaches the battery, they trigger the magnetic field. The gallium melts, envelops the battery, cools and solidifies to tightly grip it. And then they use external magnets to drag the entire solid mass safely out of the stomach tract.
They also demonstrated it for industrial soldering, right?
Yes. Imagine a complex, microscopic circuit board with a broken connection buried deep inside. You could magnetically guide a solid pellet of this gallium composite deep into the tiny, inaccessible crevice, trigger the induction heat to melt it so it perfectly fills the microscopic gap, and let it solidify. Because it's metal, it acts like a custom-fitted structural screw that also conducts electricity perfectly.
That's so smart. But wait, there has to be a biological hurdle regarding that stomach extraction concept.
Yeah.
We established that pure gallium melts at 29.8 degrees Celsius. Human core body temperature is roughly 37 degrees Celsius.
Right. You've spotted the flaw.
So if you swallow a pure gallium robot, it's just going to instantly melt into useless, uncontrollable goo inside your digestive tract before the doctors can even turn on the magnets.
Precisely. To utilize this technology inside a living human body, the metallurgy has to be adjusted. The researchers alloy the gallium with other low melting point metals, specifically bismuth or tin.
And that changes the melting point.
By creating these precise alloys, they can artificially raise the overall melting point of the composite to something like 40 degrees Celsius. That way, the machine remains a hard, steerable solid, even when submerged in 37-degree body heat, only melting when the external induction field is deliberately applied to push it past 40 degrees.
That is brilliant. But the thermal properties of gallium make it incredibly useful for other technologies right now outside of robotics. There is a fascinating application of using gallium as a phase change material, or PCM, to cool down smartphone CPUs.
This is a highly practical application of thermodynamics. As electronic processors become increasingly microscopic and powerful, thermal management preventing overheating becomes the primary engineering bottleneck.
Right, phones get so hot when you're playing games.
Exactly. Traditional PCMs, like paraffin wax or salt hydrates, have been used to absorb heat, but they suffer from incredibly low thermal conductivity. Gallium, being a true metal, conducts heat extremely efficiently.
So the design is to encapsulate a thin layer of solid gallium directly adjacent to the phone's CPU. When you are gaming or processing heavy data, the processor runs hot. That heat transfers rapidly into the solid gallium. As the gallium reaches 29.8 degrees, it starts to melt.
And here is the thermodynamic magic of phase change.
Oh.
While a material is in the process of melting, changing from solid to liquid, it absorbs massive amounts of heat energy, known as latent heat, without its own temperature rising at all. It acts like an immense thermal sponge, keeping the CPU locked at a cool, constant temperature for much longer than wax ever could.
But again, gallium throws a wrench into the engineering. It suffers from a stubborn thermodynamic phenomenon known as undercooling or supercooling. When you stop using the phone, the CPU powers down and the device starts to cool off.
The liquid gallium should turn back into a solid exactly when the temperature drops below 29.8 degrees, but it stubbornly refuses to crystallize.
Right, the data shows it remains a liquid, refusing to solidify until the internal temperature drops all the way down to a chilly 20 degrees Celsius. It requires almost 10 degrees of undercooling to finally trigger solidification.
Which is a huge problem.
Yeah, because for a phone, you want the gallium to quickly reset into a solid so it is ready to absorb heat again the next time you open an app. If it stays liquid, its heat-absorbing capacity is exhausted.
So the engineers faced a dilemma. How do you force liquid gallium to solidify at a higher, more manageable temperature?
The solution here is brilliant. It reminds me of cloud seeding. You know how meteorologists drop silver iodide particles into supercooled storm clouds to give the water vapor a physical structure to freeze onto, instantly triggering rain or snow? Or if you've ever seen those videos of a water bottle left in a freezing car, the water is supercooled but still liquid until you drop a single ice crystal in, or just tap the bottle and the whole thing instantly cascades into solid ice.
That is the exact molecular mechanism at play. They need to introduce nucleating agents. Supercooling occurs because there's a thermodynamic energy barrier to forming the very first microscopic crystal lattice. The liquid atoms need a physical template to latch onto.
So what did they use?
The researchers discovered that by stir mixing just 10% paraffin wax into the liquid gallium at 50 degrees, the wax would solidify first as the mixture cooled. These tiny solid wax particles provided that physical structure, a nucleation site, drastically lowering the energy barrier and allowing the gallium atoms to latch on and begin crystallizing rapidly.
But adding 10% wax ruined the thermal conductivity of the metal, right?
It did. So the genius refined solution was adding just 1% of silicon dioxide, SiO2, which is essentially microscopic, highly refined sand particles.
Damn.
Yeah. These tiny SiO2 particles acted as the perfect nucleating agents, forcing the gallium to crystallize and solidify at 28 degrees instead of 20. And in the practical smartphone test, this composite kept the device at a highly comfortable 34.6 degrees Celsius for over 100 minutes of continuous heavy processing use.
It is brilliant functional material science, and this molecular mastery leads us to the ultimate synthesis of these technologies. Liquid crystal elastomers, or LCEs, embedded with liquid metal.
We talked about shape memory polymers earlier, the shrinky dinks. But LCEs are the true superstars of soft robotics. They are synthetic rubbers that can contract and expand by up to 400% when exposed to heat.
But traditionally, to make them electrically conductive so a computer can control them, engineers had to stuff the rubber full of rigid metallic nanoparticles, like silver or copper dust.
And the mechanical consequence of stuffing a highly stretchable, compliant rubber with rigid, inflexible metallic particles is disastrous. It fundamentally ruins the elastomer.
Because it creates stress points.
Exactly. The material becomes stiff, loses its ability to morph fluidly, and tears easily under strain because the hard particles create stress concentrations within the soft matrix.
So, the material scientists at Carnegie Mellon replaced those rigid metallic particles with liquid metal microdroplets, specifically gallium. Because the gallium is in a liquid state at room temperature, when you stretch the LCE rubber, the microscopic metal droplets simply stretch, elongate, and deform right along with it.
You get a composite material that conducts electricity and heat perfectly, but remains as soft, stretchy, and pliable as natural biological muscle tissue.
That's amazing.
They achieved a breakthrough they term zero-stress actuation. By running a targeted electrical current through specific pathways in the material utilizing Joule heating, they can heat highly localized regions of the LCE above its transition temperature.
So only parts of it get hot.
Right. The liquid crystal mesogens in the heated regions lose their alignment and try to aggressively contract, while the unheated regions remain rigid and act as an anchor. This differential internal stress causes the entire sheet of material to bend, buckle, fold, and morph into incredibly complex, pre-programmed, three-dimensional shapes entirely on its own, with no external motors, hinges, or wires pulling on it.
It is literally synthetic muscle that bleeds liquid metal. It is mesmerizing technology. But this is where the tone of our conversation has to shift significantly.
Yes.
We now have the physical bodies. We have unstoppable shape-shifting metals, liquid armor, and biomimetic soft robots that can traverse any environment. But a chassis is useless without a brain. What happens when we take the human pilot out of the driver's seat and replace them with an artificial intelligence algorithm? Who or what is driving these things?
This is the critical juncture where we cross from the objective realm of mechanical engineering into the deeply fraught ethics of algorithmic warfare and the deployment of sentient unmanned vehicles.
Over the past 20 years, drones like the MQ-9 Reaper have become commonplace in global conflicts. But historically, a drone is basically just a very deadly, highly advanced, remote-controlled airplane. There is a human operator sitting in a climate-controlled trailer in Nevada, looking at a video feed, verifying the target, and physically pulling a trigger.
But the trajectory of defense research indicates that this human-in-the-loop model is being aggressively phased out. The sheer speed of modern warfare is outpacing human reaction times.
So they're handing the keys over to the machines.
The military is pushing the boundaries of artificial intelligence to create unmanned vehicles that essentially think, adapt, and execute like their human creators. They are developing autonomous systems capable of independently traversing complex terrain, actively hunting, selecting, and engaging targets with little to zero human intervention.
It's worth noting the fascinating and highly critical framework the university thesis author uses to analyze this shift. And just to be completely clear for you listening, we aren't endorsing this political viewpoint. We are strictly unpacking the arguments laid out in this university thesis.
Absolutely. We are analyzing the author's logic and historical framing.
Right. So they point out that this transition is part of something the Department of Defense explicitly calls the third offset strategy, initiated around 2014. And central to this strategy is a terrifying concept called prototype warfare.
Prototype warfare represents a massive, fundamental paradigm shift in how military technology is produced and deployed. Historically, the defense industry focused on the mass production of heavily tested, highly refined, and reliable weapons. You spent a decade developing a tank, subjecting it to rigorous safety and operational tests in controlled environments before you ever shipped it to a battlefield.
But prototype warfare throws that entirely out the window. It is the idea of abandoning mass production in favor of rapidly deploying experimental, unproven AI technologies directly into active battlegrounds.
It's a completely different approach.
Think of it like releasing a buggy beta version of a video game directly to the public to see how it performs, except the bugs, in this case, are lethal drone strikes. The thesis author argues that this treats active war zones, often in foreign nations, as techno-scientific laboratories. Instead of testing the AI in a safe, simulated environment, you test the algorithm's ability to identify and kill targets using live human beings in real-world, chaotic conflicts.
The underlying strategic logic here, driven by the intense international AI arms race with near-peer adversaries like China and Russia, is that the United States military believes it simply cannot afford the years required for traditional testing and refinement.
So they rush it.
They are actively leveraging special, expedited contracting authorities to get experimental prototypes out of the lab and onto the battlefield in as few as 60 to 90 days.
The thesis points to Project Maven, launched in 2017, as the true initiation of this era. Project Maven explicitly sought to integrate the private tech sector, specifically leaning on Silicon Valley and Google's expertise in deep machine learning and AI directly into military operations. The explicit goal was to develop ATR, automatic target recognition.
Right. Automatic target recognition outfits drones and sprawling surveillance networks with complex algorithms designed to synthesize incomprehensible amounts of raw data. We're talking cell phone network intercepts, high-altitude visual feeds, acoustic intelligence, thermal imaging.
And the AI just eats all that data.
The AI processes all of this in real time to autonomously decide who on the ground is an enemy combatant. The proponents of this technology argue that it vastly increases operational efficiency, drastically reduces the time needed for target execution, and theoretically minimizes collateral damage by removing human panic, exhaustion, and emotional error from the kill chain.
But the real-world data paints a deeply chilling picture of algorithmic failure. Let's look at the specific examples the author examines. There was an NSA program called Skynet, and yes, they actually named the AI targeting program Skynet.
Which is an incredible branding choice.
Honestly. It analyzed vast oceans of digital metadata from mobile networks in Pakistan. Based purely on movement patterns, call frequencies, and cell phone tower pings, the algorithm flagged thousands of people as highly probable terrorists. But the thesis points out a glaring, fatal flaw in the machine learning model.
The false positives.
Yes. The behavioral pattern of a terrorist, using burner phones, frequently changing SIM cards, traveling between specific cities, avoiding certain major networks, is algorithmically identical to the behavioral pattern of an investigative journalist trying to protect their confidential sources. The mathematical model couldn't tell the difference between a journalist and an insurgent, leading to innocent people being placed on automated kill lists.
This raises an important question, and the author also examines highly automated systems deployed by the Israeli Defense Forces, analyzing programs such as Lavender and Where's Daddy?
How did those function?
Lavender was an AI designed not just to identify militant infrastructure, but to autonomously generate mass kill lists directly from the general civilian population based on algorithmic probabilities and loose associations of Hamas affiliation.
Just loose associations.
Yes. And Where's Daddy was an automated tracking system designed to monitor these algorithmically generated targets and alert human operators precisely when the target entered their family home at night, cueing a guided bomb to strike the residence.
Proponents argue that AI is precise. But looking at these failures, does removing the human actually remove the bias, or does it just launder human prejudice and flawed intelligence through the opaque black box of a machine?
And that is the central philosophical tension of the academic paper we are reviewing. The author utilizes a political theory known as necropolitics, a framework originally coined by the philosopher Gallium Revolution.
Necropolitics.
It's defined as the ultimate sovereign power of the state to dictate who gets to live and who must die, determining whose life has value and whose body is entirely disposable.
The author draws a direct, highly provocative historical parallel to illustrate how technology automates this necropolitics. They compare modern automatic target recognition AI to the use of IBM punch card technology by the Nazi regime during the Holocaust. And again, this is the author's argument we are summarizing here.
It is a heavy comparison. The thesis cites the extensive historical research of Edwin Black, detailing how the Nazi state utilized IBM's customized Hollerith punch card machines. Before the digital era, these electromechanical machines were used to rapidly cross-tabulate massive volumes of paper census data, financial records, and ancestral registries.
So it was early data processing.
Exactly. This primitive information technology essentially automated the identification, spatial categorization, and eventual extermination of the Jewish population on a massive industrialized scale that would have been impossible using manual human labor.
The author's argument is that the 1940s IBM punch card machines and modern AI targeting systems share a fundamental, horrifying DNA. Both were developed with the explicit goal of applying automation technology to map a complex human population into politically contrived, binary classifications of who will live and who will die. The punch card optimized the Holocaust. The algorithm optimizes the targeted drone strike.
Furthermore, the author argues that prototype warfare treats human life in these conflict zones not merely as political adversaries, but as an extractive resource. In the digital economy, human behavior is raw data.
Right. Data is the new oil.
Yes. This data is extracted, processed, and used to train the machine learning models, simultaneously generating massive profits for the defense industry. Every bullet fired, every missile dropped by an autonomous system enriches the arms corporations. And crucially, the experimental data generated by that strike, whether it hit a militant or a journalist, is fed back into the system to refine the algorithm for the next strike.
It is a dark, cyclical economy of death, driven by what the author terms necropolitical data lust. The algorithm demands vast, endless troves of human behavioral data to function and improve, turning the permanent, panoptic surveillance of entire global populations into a strict military necessity.
Which brings us to a massive logistical problem for these militaries. To deploy these terrifying, autonomous, shape-shifting weapons among civilian populations or in domestic urban environments, militaries and defense corporations cannot just rely on brute force.
Because people would freak out.
Exactly. If you drop a terrifying, metallic, AI-driven spider into a city, the population will panic and destroy it. Therefore, they have to actively manipulate how human beings psychologically perceive these machines.
And that introduces the psychological front, specifically the concept of zoomorphism. Zoomorphism is the attribution of animal traits to non-animal objects. In the context of autonomous weapons, it is the deliberate design, aesthetic, and marketing of lethal robots to look and act like familiar biological animals, particularly dogs.
We have all seen the viral videos saturating social media. Boston Dynamics has a highly capable quadrupedal robot named Spot. Ghost Robotics produces a military variant called the Vision 60.
Right, the robot dogs.
They have 4 legs, they trot around with a bouncy gait, they can climb stairs, and they dynamically recover their balance if a human engineer kicks them. The way these machines are presented to the public is incredibly deliberate.
I remember when the NYPD deployed one of these robotic quadrupeds in a public housing complex, police officials literally told the press, "Digidog is out of the pound." They explicitly lean into the language of man's best friend and frame them as cute, four-legged crime fighters.
But as the thesis author points out, while the public rhetoric is totally benign and playful, the reality is that these are highly advanced surveillance and potential killing machines. Ghost Robotics actively exhibits the Vision 60 equipped with a special-purpose unmanned rifle manufactured by a company called Sword International.
Wait, really? A gun on the robot dog?
Yes. The U.S. military is actively testing these robotic dogs with mounted M4A1 carbines on their backs.
That's horrifying.
The integration goes even deeper than mounting rifles. They are integrating these zoomorphic robots with direct neural interfaces. Researchers at the University of Technology, Sydney created a functional brain-computer interface for military application.
Mind control.
Sort of. A soldier wears a commercial augmented reality HoloLens along with graphene biosensors attached to the back of their head. The soldier simply looks at a specific flickering holographic square in their visor, and the AI translates the EEG brainwaves from their visual cortex directly into physical commands that the robot dog executes.
So the soldier can steer the robot dog telepathically, commanding it to navigate a battlefield while keeping their own hands entirely free to hold their own weapon. It is genuinely mind-blowing tech, but I have to wonder about the core design. Let me just play devil's advocate here. Isn't giving a robot four legs just a highly practical engineering choice? Wheels and tank treads get stuck on stairs, they get jammed in rubble, legs can step over obstacles. Are we reading too much into the dog label? Is it really a conspiracy of psychological manipulation, or is four legs just the best way to walk over a pile of bricks?
That is the exact standard defense offered by the engineering firms producing them. However, while the mechanics of quadrupedal movement are undeniably practical for traversing uneven terrain, the subsequent aesthetic choices and PR campaigns are not accidents of engineering.
So the marketing is the manipulation.
Giving it a head-like sensor array, calling it Digidog, or leaning into the pet aesthetic is a deliberate psychological tool designed to manufacture public consent. As the thesis argues, the intersectional identity of the quadrupedal robot, the fact that it moves with the organic, familiar cadence of a dog, but thinks with the cold, networked AI of a surveillance system, creates profound cognitive dissonance in the human observer.
I see the point. The author notes that when people watch those YouTube videos of engineers kicking the robot to test its gyroscopic balance, the viewers instinctively feel empathy for the machine. We subconsciously project our deep evolutionary love and protective instinct for biological dogs onto a mass of aluminum and servos. And the author argues that this emotional reluctance to harm the robot, this induced empathy, actively masks its true identity as an agent of state violence.
To further unpack this dissonance, the author draws a fascinating, deep historical comparison, moving from the robotic dog to ancient mythology. They compare the modern autonomous drone to the Jewish myths of the golem.
Oh, I loved this part of the thesis. In folklore, the golem is an artificial creature animated from mud or earth, specifically created to protect the community from harm. The modern drone, similarly, is crafted from the Earth's rare metals, powered by silicon from the sand, created under the banner of national defense.
The parallels are striking.
But the inherent tragedy of the golem myth is that the creature lacks higher-level abstraction. It cannot truly think, reason, or understand context. It only follows literal commands with overwhelming, unfeeling physical force. And inevitably, due to its lack of understanding, it becomes a chaotic danger to its own creators.
The author uses the golem metaphor to brilliantly unpack the fatal flaw of algorithmic targeting we discussed earlier. The human drone operator sits thousands of miles away, looking at a pixelated screen. From that immense distance, the messy, infinitely complex reality of human life on the ground is reduced to mere data points and heat signatures.
So the AI is the golem?
Yes. The AI algorithm, the golem, cannot distinguish between the tactical evasion of a guerrilla fighter legitimately resisting occupation and the malicious intent of a terrorist. The golem simply executes the mathematical parameters it is given, unleashing overwhelming kinetic force on whoever sits the model, totally blind to their actual guilt, context, or humanity.
So what does this all mean? If the golem is out of control, if the liquid metal is shape-shifting and the AI is mapping the population, how do people resist this massive, creeping technological dominance? The thesis author actually created physical artworks, what they call tactical media, to protest and conceptually deconstruct this reality.
Yes, the creative physical component of their research is quite striking. They take the very materials, concepts, and rhetoric of the defense industry and weaponize it against them through art.
The first piece is viscerally intense. It is called Every Bullet Fired. The artist took discarded pieces of natural cuttle bone, a highly porous natural biopolymer, and meticulously sanded them down to the exact shape of standard military bullets.
Okay, it's natural blood.
But then, utilizing advanced tissue engineering techniques, they seeded these cuttlebone bullets with living human cells, specifically human dermatitis fibroblasts. They incubated them until human flesh grew over the shape of the bullet.
It is a grotesque but powerful critique of the necropolitical economic model we discussed. Defense companies frequently boast to their shareholders about the profit margins generated during active wartime. The artwork asks a horrific hypothetical question. If the defense industry's business model inherently relies on the destruction of human bodies to generate profit, what if the ammunition itself was literally engineered from human life?
It forces the viewer to physically confront the cold, emotional detachment of the military-industrial complex. The second piece is called Critical Mass. The artist built a series of pneumatically powered soft robots directly utilizing the soft elastomer technology we discussed earlier.
Oh, full circle to the polymers.
Right. They are made of brightly colored, highly flexible silicone cast in large X shapes. When hooked up to air compressors, they inflate, expand, and move with a fleshy, organic, almost chaotic fluidity.
The artist intentionally contrasts this soft, uncontrollable, bubbling mass with the rigid mechanical sterility of totalitarian military order. Historically, authoritarian and fascist regimes view the fluid, unpredictable nature of protesting masses or diverse populations with absolute disgust.
The rigid machine versus the fluid crowd.
Exactly. The ideal soldier is trained to be a man of steel, rigid, obedient, and rejecting of his own biological vulnerability. Critical mass serves to celebrate the entropic, uncontrollable, messy nature of organic life, inherently resisting the rigid mathematical confines of algorithmic control.
And the final piece of tactical media is the autonomous propaganda system. The artist built a DIY four-legged robot dog. But instead of mounting a machine gun or a sniper rifle on its back, they mounted a homemade movie projector, engineered from the disassembled parts of a commercial smartphone.
It is an act of technological subversion. The artist is actively questioning whether biomimetic autonomous technology is inherently destined to be used for state violence, surveillance, and necropolitics, or if the hardware itself can be reconfigured for liberation.
So it projects videos.
By replacing the lethal payload with a projector, the robot dog traverses public spaces autonomously, projecting anti-imperialist films, dissenting documentaries, and educational material onto the walls of the city. It weaponizes the technology not to kill, but to disseminate information and disrupt the narrative.
We have covered an incredible, almost overwhelming amount of ground today. We started with the raw mechanics of warfare, the evolution from Gatling guns to Mach 8 railguns, the physics of vomit guns, and the strict limitations of rigid weapons.
We moved into the incredible biological mimicry of soft robotics, unpacking osmotic pressure and the dangerous vulnerability of elastomers to extreme cold.
We explored the sci-fi reality of gallium liquid metal, induction heating, and shape-shifting materials that can melt through prison bars. And then we plummeted into the dark, ethical waters of prototype warfare, where automatic target recognition algorithms decide who lives and who dies, masking their terrifying necropolitical power behind the friendly, zoomorphic faces of robot dogs.
We have traced the evolution of the machine from a fixed, predictable iron tool of kinetic force to a fluid, highly autonomous, and potentially deeply biased agent of sovereign power.
As we wrap up this deep dive, I want to leave you with a final thought to mull over.
When you look at the entirety of the technological trajectory we've discussed today, if our materials can self-heal, if they can shape-shift from solid to liquid and back again at will, and if the artificial intelligence driving them can literally think, decide, target, and learn for itself without our input, at what point does a weapon cease to be just a tool in the hands of a human and become an entirely new, autonomous species competing with us for control of the environment?
That is a terrifying, brilliant question. Thank you for joining us on this deep dive. Keep looking closely at the technology around you, keep asking how it works, and remember, just because the surface looks like a friendly dog doesn't mean the algorithm underneath isn't calculating your pulse. Until next time.